and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective. This is lecture number 38 and the topic of the lecture is small and large signal modeling, and we will be looking into a new device which is junctionless transistor, just the basics of that. So, we have learned in the previous turn that there is an EKV model based on which the charge model is placed, and we will now develop what is known as either a quasi static and a non quasi static model. So, in basically in sub 45 nanometer era, your double gate has been the mainstay of the device technology, right. Double gate MOSFET has been the mainstay. The bulk MOSFETs are there, of course they are there, but double gate has come up in a big way sub 45, right. Now, if you want to use these devices for RF frequencies, so if this is application area is basically RF transistors or RF, then we need to develop effective models at these high frequency regions. Now, the basic assumption of quasi static analysis, if I take up, there are two types of analysis I discussed with you. So, I have a QS analysis which is quasi static analysis, which tells me that the channel charge is function of the applied biases, right. This actually breaks down. So, QS modeling or quasi static modeling assumes that the channel charge is a bias dependent, fully on the bias exclusively, and this breaks down in RF because the signals are so fast changing that the charges are not able to match the variations in the biases, and therefore we enter into what is known as a non quasi static model, right. So, we have a non quasi static model which is based on the fact, and both for small signal as well as large signal. So, if you find out the current flowing through a bulk MOSFET, it is given as mu into mu n into dVCH dx into q, right, and therefore I can write down di dx or deba, we can write down deba x can be written as w del q del t. This is the current, I is the current, right. Qi is the inversion charge, this is the inversion charge, Vch is the channel potential and inversion charge, and this is the channel quasi potential, quasi Fermi level, and mu is the electron mobility, gate width, and time and longitudinal directions are shown here. X is the longitudinal direction from source to drain. And the idea here is that since the charge has to change with respect to time, the current flowing through the device becomes a function of the space. You see del I del x coming into picture. Why? Because the charge, since at any point within the channel the charge will not remain fixed, it will be a function of time t, and that is the reason if you take a small increment in the channel and you want to find out the current in that small increment, that will be obviously a function of charge, which by itself is a function of time. So, with varying space or varying x direction, the current actually starts to vary, right, and gives you a sort of a non quasi static picture available here. Now, basically this is a nonlinear partial differential equation, and we try to solve a nonlinear partial differential solution using we try to then convert this into an ordinary differential equation, because if you take it up and try to find out, it becomes very complicated. So, good idea is to convert this nonlinear profile or into a linear profile, right, and ordinary differential equation which you can do, right, and that gives you a interesting value in terms of currents flowing through the device. If you look at the EKV model, which is the model which was initially found out, charge based model which was found out, if you assume that the double gate MOSFET is basically a long channel device and your body is basically very much lowly doped, or let me say very undoped, or near intrinsic doping has been done, then if you apply gradual channel approximation, which is a very important one, then we get Vg minus Vch to be approximately Qg by C oxide in plus Ut ln of, I will explain to you, ln of Qg square divided by 2 epsilon silicon into Q into UT into Ni plus Qg divided by Q into Ni into T silicon by 2. This is clear, where Qg is the charge density per unit area. This is charge density, areal charge density, basically areal. So, per unit area comes into picture. So, this is the areal charge density which you see, and this areal charge density sort of correlate that to the quasi Fermi level in the channel. So, Vg minus Vch is the effective voltage available in the channel, and that is related to this value of Qg. Now, you see you have a Qg squared term coming into picture, adding nonlinearity into the system. Ut is basically Kt by Q, this is equal to Ut, thermal equivalent voltage, and Ni is the intrinsic carrier concentration, Ti, T silicon is the silicon thickness, Cox is the oxide charge concentration. Now, if you solve it and do all sorts of manipulation, then we finally get that if you do a large signal, a non quasi static model available with you, then we get the total current which is flowing through the device can be written as, let me use the next slide, can be written as I equals to minus 2 times Qi plus 1 plus some value chi multiplied by dqi d xi, right, which means that the current is now actually a function of charge, variation of charge with xi, right. And if you try to find out xi, I can tell that di d this will be equals to minus del qi del tau, this is del, which means that the current and charge are related in a manner shown here, where tau is basically the sort of a lifetime. In fact, if you are very high frequency, 1 upon that gives you the value of del tau, right, and this gives you effectively the total current flowing through the device because of the non quasi static nature of the problem. So, there are many methods which are available in the device. Now, what happens is, let me now come to the device itself. When you do a small signal model, the current which you see here on the right, on the left hand side, is basically, as I told you, is a function of dqi d chi. Basically, I of I is the total normalized current and Q of I is the total normalized inversion charge, areal inversion charge. So, it is areal charge density which you see. F of Qi is a function which relates the current with the change in the variation of the dqi with respect to dxi. Therefore, the DC current equation which you get from there is, you get something like this at the bottom, which you get DC, right. Q0 basically means that when you are not applying RF signal and you have given DC bias, then the amount of current charge is given by I0 and so on and so forth. What is the meaning of perturbation analysis is that I take the DC value as I0 fixed and override over it a small perturbation I of chi bar, which is basically the variation in the current, small signal current, because of the small signal non quasi static analysis, which means that I have a DC bias here, right. I have a DC bias, and then superimposed on that I have this small signal NQS signal, and that gives you the average value to be equals to this I of bar which you see here, and that gives you what? Q0 is the DC value of the charge plus Q bar is the average value which happens because of these small signal quantities. And on the left hand side, you can also write down this to be as dq plus dq bar, correct. This gives you effective value of the total charge which you see. If you do a Taylor series expansion, I get this expression here, where we have actually neglected all higher order terms. So, all second order effects have been neglected, and I get I of xi bar becomes this quantity, and finally we end up having I equals to d of this quantity d and d xi. And I told you, therefore, the normalized form of the continuity equation is given by this, which I have already showed you in the previous slide. What does it tell me therefore? That it tells me therefore that when you apply a non quasi static model, unlike quasi static model, since charge is time dependent quantity, the current also becomes time and space dependent quantity. So, if you take any elemental value within the inversion layer of the device, you will see that it depends both on the charge as well as on the space. Both space and the time factor is always there for a device. This gives you a basic idea about the expression. Now, what I do, if I put now the total current to be equals to I0 plus I bar, which I have shown here, and I0 is the DC current plus I bar is the non-quasi-static current because of the small signal input voltage, and Qi to be equals to Q0 chi plus this thing. This is again DC plus perturbation I have added, and as I told you here, I and Qi are the total current, whereas Q I naught are the DC quantities of I and QR, and they are small signal. So we write down this to be as dQi is equals to this thing, average value. Actually, if you look at the charge will vary with respect to time, right, and with respect to space. What we have done is that within that small increment of tau, where the signal is moving very fast, I take the way to model it is like I take an average value of the charge there, right. When I take an average value of the charge, mathematically it becomes simpler to handle it in a sense, and we write down this expression as di of d xi to be equals to minus j omega n q, where omega n is the normalized frequency of the what, of the input signal. And similarly you can write down that d of xi dq is equals to f of q0 upon I0. Everything has been taken from, most of the explanations and documentation has been taken from this paper, right, and gives me effectively the DC current equation can be written as shown at the last page of this slide, right. Now after simplifying the equations, I get this z is a function. Do not worry about all these things, this is quite complicated in nature at this first stage. I want to give you a brief idea of how to proceed numerically as well as analytically, and we try to find out the solution of the current, and this comes out, the solution of the current comes out to be this one, right, and this is the average current which is flowing through the device, and it is a function of many factors like the Bessel function, the 1 by minus j 1 by 2 minus 1 by 2 is the 1 by 2th order Bessel function which is there, and then we get differential equations and we get these values of g of q0 as this at this particular point. Now what we try to do then is we try to find out the charge perturbation qi prime, and the charge perturbation qi prime is given by this formulation, right. I do not want to go into details of this, but from a purely physics point of view, which is written here is we try to find out the difference between the steady state and the non-steady state. So the difference between them will give you the average value of q bar, and if you substitute the value of qs bar and qs into the original equation, I get the total value to be equals to qs bar and qd bar. So this is basically my charge perturbation at the source end, and this is the charge perturbation at the drain end, right, and from here I can get the value of C1 and C2 by knowing, which means that if you know very carefully, in MOSFETs as well as in double gate MOSFETs, the charge, how the charge partitioning is done between source and drain is still a topic of research, though much clarity has come. So when you switch off your double gate MOSFET or a single gate MOSFET, how much charge goes to the source end and how much charge goes to the drain end is still not clear. Similarly, this expression which you see here is an approximate expression giving me the value of the source and the drain side perturbations there. From this we can get the value of C1 and C2. Looks complicated, do not worry of the form of the complication here, and then we try to find out the total current as IS and ID, right, from the Y parameter modeling, where this current is the small signal current which is leaving the device through the terminal, and this is that entering the device. So the difference between ID bar and IS bar will give you the net current which is flowing through the device, right, and this will be obviously a function of the time as well as space. Both the expressions will be a function of time and space, right, and gives me a rough value of the total current flowing through the device. Now the fundamental charge based Y parameter model is given by these two expressions here which you see, both the source and drain end, and as you can see interestingly both at the source and drain is very symmetrical in nature. Only thing you need to ensure is wherever you are encountering the source charge, you just plug in the drain charge there, and the expressions remains almost symmetric in nature. And if you solve it for the double gate MOSFET and normalize it with respect to space and voltages, I get small signal Y parameter model. This is the quantity which is shown below, which is YD, YSD, YDS, right. So this gives me at least the basic idea of an uh, at least the unnormalized part of the y parameter. Later on, if you look at this research paper, later on the authors have gone ahead and have shown also the normalized part. So, what I wanted to showcase to you as far as this work was concerned, or this idea was concerned, was to give you a brief idea about how the modeling of a double gate MOSFET is done in various methodologies. This is an analytical model which we have tried to find out. Now, with this, let me come to the last class of this thing, and that is basically the junctionless MOSFET, which we will do. So, we will try to introduce to you the junctionless MOSFET, look into the fabrication of FET and challenges of junctionless MOSFET. Now, if you look at the left hand side figure and the right hand side figure, the left hand side figure is basically my junction MOSFET, because I have an N plus plus layer here, let us suppose. I have a P type layer here, and I have an N minus layer which is sandwiched between N double plus and P type, right. It is sandwiched between N double plus and P type. So, if you look very carefully, these are junction transistor. Why? Because now you will have a depletion being formulated both at these two junctions, at this junction and at this junction. You will have depletion regions here and here. Similarly, you will have here and here, depending upon the type of doping which you have done. We generally do abrupt doping profiling when we do conventional junction, and therefore it employs a costly and complex annealing process. However, junctionless FinFETs or junctionless double gate MOSFETs implies uniform doping profile in the source and drain region, simplified fabrication procedure, right, which means that if you look at the right hand side figure, it is a junctionless double gate transistor, where this is the top gate, this is the bottom gate, and you see the whole of, there is nothing like channel being formed there, the whole region is basically N plus region, right. So, there is no junction being formed here. So, it is basically silicon doped with fifth group element, and to generate N plus layer, you can also generate an N double plus layer also. So, when you give a gate voltage positive, not have an inversion layer, right. If you look very carefully now, if you give a drain voltage, you will have a current flowing, because it is just large number of charge carriers available. You have to give a gate voltage to switch it off when you might want to deplete the channel between source and drain. The advantage is low cost, which you see. So, as I discussed with you just now, that the density, the device is basically a resistor, right. If you go back to the this thing, it is basically a resistor. From this edge of the device to this edge of the device is purely a resistor, and the resistivity of the resistor can be changed by applying the appropriate bias by the gate. Now, since there are no junction being formed, and since there are no depletion region, the mobility is relatively high. So, the currents are very high. This is one thing. The another advantage is that since there are no junctions, since there are no depletion region, the dissipation of heat is also much better in case of a junctionless device as compared to a junction device, right. So, let us look at the fabrication step. The first fabrication for the junctionless was 2010. J.P. Coolidge was the person, and characterized by a silicon thickness of 10 nanometer, and channel length was 1 micron, which is quite big. So, if you look very carefully, this was the gate, right. So, on the right hand side, this is the oxide layer which you see, this is the oxide layer, and this is silicon nanowire. Silicon nanowire basically means sheet of silicon being introduced. So, there is no source and drain, other regions are there, right. And this is used, so SOI technology is used to produce this high quality single crystal silicon film with thickness of few nanometers. Now, this is quite critical. Now, you have to be very cautious that the silicon nanowire should be very thin, because you want it to be inverted at a very low gate voltage, and the material quality used in silicon nanowire should be also of high quality, so that you do not have any traps or extra impurities being inserted within the silicon nanowire, right. That is very important to keep in mind. So, what people did, that if you use a commercial SOI wafer, use an e-beam lithography, and we can actually convert them into nano ribbons, and then which are basically about 5 to 10 nanometer thick design which you look. You can also grow an oxide layer, and the nanowire uniformly is doped by ion implantation. You can do ion implantation or even simple fixed doping here. Since you can use arsenic for N type, and generally we use BF2 to generate p-type devices for junctionless transistors, right? And this is what we need to show. Now typically we have taken it from this research paper that the implant energies which you do for the Gaussian implants, you should have an uniform doping concentration ranging from 2 into 10 to the power 19 to 5 into 10 to the power 19 atoms per centimeter cube for different wafers, and such high doping levels are traditionally reserved for source and drain doping in the conventional CMOS process. In the gated resistor, the high doping is required because you require a high current, right? And you understand the point, no? So if you do a high doping, there will be large number of free charge carriers available there, and therefore there will be a good large current flowing through the device. So current drive will be much higher. Further, since there is no junction, there will be good source and drain contact. The gate is generally formed by using a 15 nanometer thick layer of amorphous silicon at a temperature of about 550 degrees centigrade using a low pressure CVD reactor. After that, a P plus and N plus gate dopant ions with a dose of 2 into 10 to the power 14 per centimeter cubes are there, and then you are annealed in a nitrogen ambient for 900 degrees centigrade. Why do you anneal it? Because why do you anneal it with nitrogen ambient is you do not want oxidation species to be sitting within that and generate extra traps there, right? And that is the reason you do it, and you anneal it for approximately 30 minutes in order to get this dose available with us. Now, so what you see is here is then what you do a reactive etching. What you do reactive etching is the gate electrodes, which are metal gate electrodes, are patterned using an RIE reactor. So after the gate patterning is done, then you grow a layer of silicon dioxide. When you grow a silicon dioxide, that acts as a passivation layer, right? And then you can draw contact holes are etched, and using aluminum metallization process, you can provide electrical contact to the device. So if you look at the left hand side figure here, it's basically 5 parallel devices, 1, 2, 3, 4 and 5 parallel devices with a common polygate. So you see this is the common polygate which runs across all these junctionless transistors, and these black colored are basically your nano ribbons. So there are 5 nano ribbons, and surrounding it is a buried oxide, right? And above it is the polygate. So if you give a polygate voltage, the current will be flowing through the junctionless transistor. Now this is basically a magnified image of a single nano ribbon device, and which has got atoms being formulated. So if you look very carefully here, you will see that they are all arranged in such a nice manner, very regular manner, right? At a very regular manner they are arranged, and that adds to the value of a junctionless transistor, that it gives you a very high current at a much lower threshold voltage. But let us see what are the issues and challenges in a junctionless FET. Obviously there are performance issues, because though we supposed to reach that speed, we are not able to reach that. Then there are large issues with variability, right? And that is a significant challenge, because as we have seen, the junctionless FET can operate very well provided you maintain uniformity and non-variability in your production process. But that is not the case. There is always a issue of variability coming into picture, which actually degrades the characteristics of a junctionless FET device. Now, in order to increase the drive current, you also do high doping, right? However, while doing high doping, you end up having a large IOF, or the off current or the leakage current. So what happens therefore is your ion by IOF does not go up significantly, it remains somewhere lower value. So you expected it to go high, you are not going high because of high dopant concentration available here. So with this what we do is we will recapitulate what we learned in this thing. We learned about junctionless transistor, the advantage of junctionless transistor, how junctionless transistors are fabricated, what is the meaning of a highly well defined nano ribbon or a silicon nano ribbon. If you go back again, I will refer to this TEM image here. You see the atoms are spaced in a very nice periodic fashion. If this would not have been the case, then the advantages of junctionless would actually be offset by large variability and issues with respect to the nanowire which is drawn there. Moreover, the barium oxide which you do over the silicon nanowire should be such that this does not allow to have a large number of traps within the system. If that happens, then the current gain becomes small. So the gain which you are getting because of junctionless can become offset by large trapping density here, right. That is the one basic disadvantage of a junctionless transistor as compared to a bulk MOSFET. So we have done that. So we have learned the flow, fabrication, the process flow, right. We have done the process flow. We looked into the challenges, right, and the challenges which we faced, which you will face if you do a junctionless fab, and then junctionless fab MOSFET, right. Maybe a DG also you can do. And we saw that finally we saw that if this is the case, then the variability issues become a major challenge in a junctionless device. So with this we will stop here, and when we meet next time we will go into a new chapter of devices. Thank you very much.